I'm Paolo Zappalà, and I will present you this joint work with Marianna Bellotti, Maria Potabuttucaro, and Stefano Secci. We will talk about game theoretical models for blockchains. Specifically, we introduce a new game theoretical model whose aim is to provide an analysis of the robustness of a blockchain system. First of all, we provide the tools to the model a general protocol composed by different modules. And finally, we show some of its applications. So blockchain systems rely on the fact that users follow the protocols, which stand at the end at the basis of the technology itself. In the current literature, the robustness of a blockchain protocol is proven through a game theoretical concept called Nash equilibrium. So let's see this example. We have some player, which represents our users, and every single player has different strategies. One of these strategy is the one that represents the protocol, so it's the one with the star, the green star. The others are different strategies that are default marked as malicious. So a Nash equilibrium, and a protocol represents a Nash equilibrium when a single player is deviating alone, is receiving a lower utility. So this concept, if this happens, these concepts correspond to a stable solution. And so this is called, thought as a robust enough, a protocol is robust enough. Another consideration is made towards attacks. So there might be also other Nash equilibria, like in this example, we have 3 players which play malicious strategies. And if they change, or if just one changes her strategy, he gets a lower utility. So in this case, we have another Nash equilibrium, but this is not the one corresponding to the protocol. So this is called in literature an attack. Of course, in literature, there are other concepts of attacks, also the properties, other even concepts of equilibria. But in our opinion, no model aims at providing a comprehensive model for the analysis of the robustness of blockchains. So we would like to show our approach. First of all, we consider not only one, but any number of possible deviating agents. And second, we distinguish the deviating behaviors of the agents between rational and Byzantine. So rational agents are those who follow the protocol because they want to increase their utility, while Byzantine agents can generally choose any kind of strategies which is different from the one of the protocol. So we introduce some definitions which are already known in literature, which we need to understand how robustness is analyzed. So first of all, the protocol is represented by a pair called mechanism, which is formed by a game, which represents the situation with all the players and all the possible strategies, and a joint strategies, which represents the protocol itself. So every single player who follows the protocol has to play these specific strategies. So first of all, we analyze rational agents, and we have two different properties that represents the robustness of a protocol. So the key resilience means resilience equilibrium means that there is no subset of users, of players that can deviate in order to increase their utility. So they can have a joint, instead of just one, can have a joint deviation and altogether change their strategy in order to get a better equilibrium. While practicality is a property that avoids that says that the mechanism consists in not playing weakly dominated strategies, which are strategies that provide a smaller utility than a different strategy which is dominating. So what we prove in our work is that the two properties are independent, and therefore it's necessary to analyze them both. And secondly, we analyze the Byzantine agents, and there is a problem literature which is called T-immunity that says that the protocol provides the very same outcome no matter what a subset of TU players does. This property is interesting, but we think that is very rare to be applied. Sometimes it is very rare to be found, and therefore we introduce a new property which is called T-weak immunity. And basically what we do is to set the value, the utility of the initial state to 0, and then we want that the protocol provides at least the utility of the initial state, which is null, and no matter what the subset of T players does. So we find that this property is easier to be detected, and also is more often found in a practical situation. So some protocols are made by different independent components, and our method of analysis consists in analyzing them separately with different games. So that's why we introduce an operator which is called composition of games, which basically consists in playing 2 or more games at the same time. What we do, and we prove that the operator preserves all the properties. So we can study all the single games separately, find the properties, and then thanks to this property, we can know that the whole protocol preserves the very same properties. So thanks to this method, we analyze different protocols, starting with a 2-layer protocol called Lightning Network, and we deployed the game theoretical model to prove that one of these modules, the closing module, does not fulfill the property of weak immunity. And then thanks to this method, we also provide an alternative, which satisfies, of course, the property of weak immunity. Then we analyze a sidechain and a cross-chain swap protocol, and we prove the very same properties. So let's go a little bit in details. So what we did is analyze a single protocol. In this case, is the protocol to update the channel in the Lightning Network. We model it with the mechanism. So in this case, you see the game tree, and all the players can do at every single step. And then we define a mechanism, and we prove the properties thanks to the theorems. So let's consider another example. This one is the cross-chain swap. We have 2 players, Alice and Bob, who want to exchange 2 assets belonging to 2 different blockchains. So we have the yellow blockchain on top, the first one, and the second one green. And there's a protocol that allows to exchange 2 assets onto different blockchains. So we consider the protocols. Here is in a simplified version. We mark the action belonging to different blockchains. So we see in this case the yellow one for the first blockchain and the green one for the second blockchain. And we can split every step to see which one are applied on one blockchain or another. So we have 2 different, I would say, protocols depending on which blockchain is analyzed. So the first one and the second one. And then, since the 2 blockchain dependent, we can consider 2 different games, which are shown in figure, and evaluate the single properties, create a mechanism, evaluate the properties, and then exploit the property of the composition of games to prove that the whole protocol is robust. So this analysis lets us get an easier tree, which is easier to be analyzed, and then prove in an easier way all the properties. So summing up, we'd like to introduce a different approach to analysis of robustness of blockchains, and we provide some indices which are clear to be understood, and we believe that this can help in identify the risk of deploying blockchains in certain circumstances. So we provide some tools and some theoretical tools, and show that it can be applied in some specific application. And in the future, we would like to extend it to different protocols. We saw some examples, but one we like to extend to more known protocols. So thank you very much.